Have you ever just stopped and watched the shadows get longer and shorter during the day? Or maybe you've noticed the constellations you see in the dead of winter are totally different from the ones you see in the summer. Well, these are all little clues to this huge cosmic dance that's happening between the Earth, the Moon, and the Sun. So today, we're going to break down the simple but pretty profound movements that shape our days, our years, and even create some of those spectacular events we see up in the sky.
Okay, so let's dive right in with the big question, the one that probably started it all. We see the sun rise in the east, travel across the sky, and set in the west. I mean, it really feels like it's moving, right? But we're always told the Earth is the one moving around the sun. So what's the real story? Is the sun doing all the work, or are we?
All right, the first piece of this whole puzzle is our planet's daily spin. This is the one movement that defines our most basic rhythm of life. You guessed it, the cycle of day and night.
You know, this isn't some new idea. We've actually understood the basics for centuries. The ancient Indian astronomer Aryabhata absolutely nailed it with this boat analogy. It's so perfect. When you're moving, everything that's standing still looks like it's moving past you. Well, that's exactly what's happening to us here on Spaceship Earth.
Think about it like this. Remember being on a merry-go-round as a kid? As you spin around and around, the trees and the people standing still, they all look like they're whipping past you in the opposite direction. Well, we are on a giant, planetary-sized merry-go-round. The sun and the stars are just sitting there, and it's our spin that makes them look like they're moving across our sky.
So, the official word for this very specific kind of motion is rotation. All it means is that the Earth is spinning on an invisible line, what we call its axis, that goes straight through the North and South poles.
And this spin isn't just happening randomly, it's got some very specific rules. Our planet rotates from west to east, which is why the sun appears to rise in the east. And it takes about 24 hours to do one full turn, which, no surprise, gives us the length of our day. The most obvious effect of this whole thing, that constant, reliable cycle of day and night.
And here's how simple it is. As the Earth spins, just picture it like a big ball being lit by a single lamp. That lamp is the sun. The side of the ball facing the lamp is bright. It's in daytime. The side facing away from the lamp is in its own shadow, and that's nighttime. It's really that elegant.
Okay, but what if you wanted to prove the Earth is spinning without, flying into space? How could you do it? Well, back in the 19th century, a guy named Leon Foucault came up with something absolutely brilliant. He built a massive pendulum. As it swung back and forth, it looked like it was slowly changing direction all day. But here's the crazy part, the pendulum wasn't changing at all. It was the floor and the entire Earth that was rotating right underneath it. What a simple, powerful proof of our daily spin.
Okay, so rotation explains our day. But what about the year? For that, we've got to zoom way out and look at a second, much, much bigger motion.
So here's the next logical question, right? If we're just spinning in place, shouldn't we see the exact same background of stars every single night? But we don't. We know that a constellation like Orion is a big star of the winter sky, but come summer, it's gone. Something else has to be going on.
And that something else has a name, revolution. Now, this is a totally different movement from rotation. This isn't the Earth spinning on its own axis. This is the entire planet traveling along a path, an orbit, around another object. And in our case, that's the sun. And this is what perfectly explains that changing night sky. As the Earth moves from one side of the sun to the other throughout the year, the direction that our night side is facing out in space changes. So, in June, our nighttime faces one slice of the cosmos. By December, we've traveled halfway around our orbit, and now we're looking out at a completely different part of the universe, with a whole new set of stars.
So, we've got rotation for the day and revolution for the year. But what about the seasons? This is where we get to the most important little detail of them all, our planet's tilt.
Let's just tackle a really common misconception right away. A lot of people think, hey, it's summer because our part of the Earth is closer to the sun. I mean, it sounds logical, but it's just not true. Let's see why.
The key here is not our distance from the sun. That actually doesn't change all that much. The real reason, the entire reason we have seasons, is the tilt of our planet's axis. See, Earth doesn't spin perfectly straight up and down. It's tilted over by about 23.5 degrees. And that little tilt is the engine that drives everything.
And here is where it all clicks into place. As the Earth makes its year-long journey around the Sun, that 23.5-degree tilt stays pointed in the exact same direction in space. It doesn't wobble around, which means for one part of the year, the northern hemisphere is tilted towards the Sun, and for the other part, it's tilted away.
Now, this tilt has two huge effects. When your half of the world is tilted towards the sun, the sunlight hits it more directly. It's like a flashlight shining straight down on a spot. It's concentrated. It's intense. Plus, the days are longer. That's summer. 6 months later, when your hemisphere is tilted away, that same sunlight hits you at a sharp angle and gets spread out over a much larger area, which makes it weaker. And the days are shorter. That's winter.
Now, for the grand finale. What happens when all these predictable movements, the rotation, the revolution, cause the Earth, the Moon, and the Sun to line up in a perfect, shadowy, cosmic coincidence?
Well, when these guys get into perfect alignment, they can actually cast shadows on each other, creating some of the most jaw-dropping events we can see from down here on Earth, eclipses.
But wait a second, how in the world can our tiny moon possibly block out the enormous sun? It's all thanks to an absolutely fantastic cosmic coincidence of size and distance. The sun is about 400 times wider than the moon, but it's also about 400 times farther away from us. And because of that, their apparent sizes, how big they look to us from here, are almost exactly the same. It's incredible.
So, there are two main types of eclipses, and it all comes down to what's casting the shadow on what. In a solar eclipse, the lineup is sun, then moon, then Earth. The moon gets in the way, and its little shadow races across a tiny part of the Earth. But in a lunar eclipse, the lineup is sun, then Earth, then moon. Our own planet gets in the middle, casting its huge shadow over the entire face of the moon.
And get this, people have been predicting these events for a very, very long time. This wasn't magic, it was math. Ancient astronomical texts, like the Surya Siddhanta from India, had these super detailed calculations that let astronomers figure out exactly when these amazing shadows would fall, with truly impressive accuracy.
So, we've covered the daily spin, the yearly journey, and the incredible shadows they can create. I want to leave you with one last thing to think about. We've seen just how incredibly important our planet's tilt is. So, what if it wasn't there? What if the Earth's axis was perfectly straight up and down? What would happen to the seasons then? What would life on Earth even be like? Something to chew on.